Hi, I'm Mark Pelland,
I'm Jeremy Partaker.
and we're members of Base 2. We did our block stacker as our project for digital logic systems last term.
So unfortunately we're missing two group members, Brandon Hill and Ryan Crook, and we just wanted to mention them because they had a big contributing part to our project. So just a summary of our features real quick. We'll explain them in the following slides. We have our PS2 keyboard input. We have a module for generating random blocks, a module for rotating their block clockwise, for shifting blocks left, right, and downwards, which is both automatic and manual, and I'll briefly talk about that. Checking for collisions, auto deletion of rows, and displaying game on LCD display.
When we started our project, we thought it would be useful to have some direction, so we made a flowchart, and we just kind of used that for guiding how we programmed and structured our project.
So when you press a key, W, A, S, or D, it's pretty much a string of serial bits that are sent from the keyboard and for an action, and that's our input. That's our main user input. We also have a 50 megahertz clock signal from the FPGA, and we will use that to divide. We will divide that actually, and use that for the implementation of the auto shift downwards. We also have an LED output, which is blinking to show this divided clock speed, and our VGA output. So for PS2 keyboard, when you press a button, it's sent in a string of serial bits. Start and end bit are pretty much arbitrary. We have a parity bit which checks for error, and these data bits from 0 to 7 just correspond to correspond to a hexadecimal number, which is an ASCII code and corresponds to a key on the board. For generating our random blocks, we have 7 choices, and we count from 0 to 6 really fast with a clock signal, and we just pick a number randomly, and that corresponds to one of our 16-bit vectors that are there. So for rotating our block clockwise, you can see visually and logically how it's done. We pretty much just transform it using a matrix, which transforms the sprite.
As for shifting the blocks, once we have our rotated sprite, we just break it into separate rows and then pad them with zeros to make one large vector. So the point of this is once you've got that long vector, it's just a matter of shifting it into the game field, which is also a vector. So you can see how sequence, which is just your sprite broken up and padded with zeros, can be shifted in from the left into V1, which is your game field. Whenever there's motion that's being produced, so either when the game is shifting the block down or when the player is produce an action, there's always a comparison between the position of the falling block and the position of existing blocks that have already been placed. So if there's a collision between those two, then we have recorded the previous position of the falling block, and we don't allow the new position to be committed to. Row deletion is just accomplished by ANDing all the bits in a given row, and when that AND becomes true, it means the row's full, and then we shift all the above rows down by one row. The VGA display is just code that we got off the internet. It needed to be adapted so that it would display the game field, and it reads off the large vector that we have of all the falling block and the existing blocks on the screen.
So we did have some future improvements that we unfortunately didn't have time to implement, and they're just visual and improvements to the game that we could have done to make it a little better. So we'll just give you a demonstration real quick of how our block stacker game works. So you could just see the automatic shift from the divided clock signal shifting the block automatically downwards. I'll start to play a little bit here. A and D shift the block left and right, and S speeds up the movement downwards if you want to speed up the block. I'm just going to try here to make a full row to show the auto deletion.
So one of the advantages of using a keyboard and a VGA display, despite it seeming, like kind of like a big extra, is that you get to work to a standard, and that actually turns out to be a positive thing because you have plenty of documentation that explains how to set it up, and you already have devices which are compatible with it. Like for example, we already had a keyboard, so our method of input was our device for input was already fabricated, and we just used pretty much any monitor, or in this case we're using a projector for displaying, like presenting our project. And Jeremy's trying really hard to get a full row.
There we are.
Okay.
So it just deleted the rows that were full by adding them all together and making them true. Yeah, so that's our digital logic game. Hope you enjoyed. Good luck on your project.
And
Thank
have
you
fun.
for watching.